Okay, the next functional group that we are going to learn in this chapter will be amides. Okay, because amides contain a nitrogen also, and this chapter where all the functional groups are organic nitrogen compounds, right? Okay, so amide functional group C, O, and H. So if you write the structural formula, then the functional group will look like this. But if you have to show the bonds, okay, CONH is C double bond O, and okay, and this H, okay, should be on the opposite side of this double bond O. Now, because of the repulsion between the electrons, okay, to minimize the repulsion, CO and H will actually always be arranged this way. It is not correct to put them on the same side. Okay. Now in the mark scheme, okay, the way they mark the structure of amides are becoming very strict. They don't accept O and H on the same side. They must always be on the opposite side because of the repulsion, right? So must be like this. Okay, now so any organic compounds with functional group C, O, and H, okay, is called an amide. Now look at this N. This N is bonded to one H, okay? Here, sorry, in this compound 2H. But actually this N can be bonded to 1H, okay, 2H, 1H, 1R group, okay, or both also R groups, LQ groups. They are still, okay, they are all still amides. So as long as you see C double bond O bonded to an N, okay, the N has hydrogen or LQ groups, okay, then you can recognize, you'll be able to recognize that they are amides. Right, the naming of amides are actually not mentioned in the syllabus, especially this with the N. Okay. Now, but sometimes in the question they will give you the name of amide. How do we know it's an amide? It will end the name. If you look at the name, it will follow the number of the carbon. Here we have two carbon, right? Two carbon atoms. So if this is an alkane, we name it as ethane. So how to distinguish them is after ethane, they'll add an amide word, okay, at the back. So you know at ethane amide by looking at the suffix, you know that it is actually an amide. Okay, this one no longer in the syllabus, so let me cancel it. I forgot to delete it from the slide. Now let's look at the property of amide. This point is very important. Amides are neutral. Yeah, very important, neutral. If you look at the structure of amide C double bond or NH2 in this molecule, you would think that this NH2 is just like an amine. The nitrogen has lone pair electrons. So this nitrogen should be able to accept proton. So amide should be basic. But actually, okay, but I'm telling you here, amides are neutral. So why is it neutral? Does it mean that the N with the lone pair will not be able to accept proton? Yes, okay, it will not be able to accept proton. I'll tell you in the next slide. Okay, now let's look at the last point of this slide, which is the preparation of amide. We usually prepare amides from reaction between acyl chloride and ammonia. Okay, because acyl chloride is much more reactive compared to carboxylic acid. So using acyl chloride will actually give us higher percentage of yield and also higher rate of reaction. So we actually will be able to make amide faster. So again, preparation of amide will be from acyl chloride and ammonia. Now, of course, if you want this one to be, let's say, CH3, CON H and then CH3, then you have to change ammonia to a primary amine. So it all depends on which amide you want to make. Okay. Now go back to the properties of amides. They are neutral. Why are they neutral? Okay. So this is the structure of amide. Okay, one amide like this. And this lone pair of nitrogen, since amides are neutral, that means the lone pair on this nitrogen cannot be donated. So why is it not available to be donated? Is because this lone pair of nitrogen can be delocalized. So when it got delocalized, it forms a structure like this, the one on the right hand side. Now this nitrogen doesn't have a lone pair anymore, it carries a positive charge. Okay, and then this C double bond O initially in the compound, it was C double bond O. The pi bond was broken, okay, and then now O has three lone pairs and carries a negative charge. So these two structures are actually in equilibrium with each other. So sometimes you have the lone pair on the nitrogen double bond, okay, between CO, but sometimes this lone pair, okay, lone pair is in the p orbital of the nitrogen. So it overlaps with the p orbitals from this carbon. So this carbon has double bond, so I mean it has an unhybridized p orbitals. So when the p orbitals of nitrogen and carbon overlaps, right, the lone pair of nitrogen which are in the p orbital can be delocalized. So because this delocalization, okay, this lone pair electrons on nitrogen is actually not available to be donated. So it cannot accept proton. Therefore, amide is actually not basic. Okay, it is neutral. It doesn't behave like an acid or a base. Now, I have to emphasize that this is actually not required. This explanation is not required in the syllabus. Okay, what is required in the syllabus will be, okay, knowing that amides are neutral. Okay, amides are neutral. The only explanation that you need to give is, I have a question later, right? The explanation is because, okay, here, suggest why this amide has a pH of 7, neutral. Due to the lone pair on the nitrogen being delocalized. So that's all. That's the only explanation that you know. So it kind of like it is kind of like consistent with all the explanation that you have learned before this part, okay, before this topic. You learn the acidity, comparing acidity of different acids, comparing different basicity of amines, ammonia, and also phenylamine. Okay, it's always about delocalization of electrons. So if you are able to apply this delocalization of electrons in the structure of amide, okay, then okay, you'll be fine with this explanation why amides are neutral. Okay, now I have a very interesting question that I took from this winter 19 paper. It gives a structure of an amide. It's called nicotine amide. So this nicotine amide has a six-membered ring. Why they call it six-membered ring? Because you count the number of atoms that is forming they are forming the ring. One, two, three, four, five, six. Okay, six atoms forming a ring. That's why it's called a six-membered ring, including the nitrogen. Then after that you have the CO and H2, right? This part makes this molecule an amide. Part 1. State the number of delocalized electrons in one nicotine amide molecule. So by looking at this, it of course reminds you of a normal benzene ring, right? So in one normal benzene ring, okay, all of them are carbon. In this case, you just replace one of carbon with nitrogen. But this circle still means three double bond. One, two, three. Okay, like this. Like in calculate structure, you have the three double bonds. So there are six pi electrons here. Although they turn one of the carbon into nitrogen, this circle still means three double bonds. Yeah. So there are still six, okay, six pi electrons here in this circle. Now, if you look at the 3 points, electrons from the carbon atoms in the this delocalized system includes electrons from the carbon in the six-membered ring, Okay, so all these carbon, the electrons are delocalized, so 6 pi electrons. And the 2 electrons in the pi bond of the C double bond O, or somehow, okay, the pi electrons here are also delocalized into the ring, so plus 2. Okay, plus the 2 electrons in the lone pair on the nitrogen atom of the amide group. It seems that this lone pair on this nitrogen in the amide group also delocalized, so plus 2 more electrons. So altogether, we have 10 electrons in the delocalized pi system. So the answer to this part is 10. Yeah, I'm showing you this because I find it very interesting that they ask you to find the number of delocalized electrons, where in just one simple molecule like this, you have so many electrons being delocalized into the ring. Okay, just find the sum of all the delocalized electrons, then you'll be able to answer this question. Now, second part, predicting the bond angle is also interesting. Nitrogen, okay, here they are talking about this NH bond angle in the NH2 group, this one. Now, usually if you look at ammonia, okay, 3 bonds, right? It has a lone pair. So if you look at ammonia, you know the bond angle in ammonia is 107 degrees. So by looking at this, you'll be thinking, oh, okay, this N bonded to H, bonded to H. Okay, also bonded to this whole big group. Just name it as R. You'll be like, is this the same like ammonia, right? It should be 107. Okay, and if you write 107, your answer is not correct because you forgot. Okay, in this case, you have to remember that the lone pairs are actually delocalized. Delocalized means, okay, the lone pair is here or into the ring, right? It's no longer on top of this nitrogen. It's not near on any of the bonding pairs, so the repulsion is not so great anymore like in ammonia. Okay, so if I tell you that there's no lone pair, what if I tell you that there's no lone pair on this nitrogen? Okay, you wouldn't predict that the bond angle to be 107. Imagine there's no lone pair here. Okay, and you know that all 3 bonds will be equally spaced out. The bond angle will be 120, right? So that's exactly what happened in this amide molecule. No lone pair because the lone pair is delocalized. Therefore, this bond angle is actually 120. Okay. Now you know why I chose and include this question because it requires a bit of thinking about delocalization and not very ordinary like just comparing it to an ammonia molecule. Okay. Now because the delocalization lone pair no longer belongs to only nitrogen, weaker repulsion, therefore okay, equally spaced out and you get 120 degrees. Okay, right, so that would be discussion on this question. Next is we are going to look at how do we prepare amides. I already mentioned this, in the last part of the first slide of amide. Okay, acyl chlorides and also ammonia will react and give you amide. So they are prepared by reacting acyl chloride with concentrated ammonia or amine, and you get amide as products. So this is acid-base reaction. And what do they expect you to know from here is, of course, the reagents, which is the ammonia or amine, depending on the amides they want to make. And also, you must be able to write an equation. The equation is not very complicated. You remove the Cl from acyl chloride. Okay, you plug in the NH2. And then, okay, initially you start with ammonia, right? Ammonia has 3 hydrogen. But in amide, only 2 hydrogen. So 1 hydrogen is removed. HCl is removed. So they combine together and form the byproduct HCl. So So byproduct is always HCl because you are using acyl chloride. So knowing that, okay, always remove one H from nitrogen, remove the Cl from COCl, then you combine the other parts together, you get the amide, and then HCl is the byproduct. Now, because acyl chloride is very reactive, this reaction will occur at room temperature. Doesn't require any heating. Right, the next reaction of amide will be hydrolysis of amide. Now, this reaction always reminds me of hydrolysis of esters. Okay. Let me just add one more slide, and we always use something that you have already learned, okay, to relate to something that is new, so it's easier for us to link, okay, everything together, or use something that we have already mastered to learn the new one. Okay, sorry, I should just remove this whole thing. Okay, much better. All right. Okay, here. Okay. Now, hydrolysis of ester. Okay, let me draw a molecule of ester. So if I tell you that I need to hydrolyze this ester, what will you do is, okay, you will actually break ester, okay, between the C and O, then CH3COOH, and then CH3OH. Okay, you break it down back to its original carboxylic acid and also alcohol, because ester was made from the reaction between carboxylic acid and alcohol. Now, amide also the same. Amide was made, okay, from acyl chloride, okay, and ammonia. Okay, let me draw the structure of this amide. So now I'm telling you, I want to convert this back to acyl chloride and ammonia. So what can I do, right? Okay, I take this amide, okay, I do hydrolysis. So I have a break between these because they were joined there from the reaction. So CO, okay, then NH3. But unfortunately, we won't be able to go back to acyl chloride, okay, by using hydrolysis. Why? Because hydrolysis means you use water for the reaction. Can you look at water? Okay, you can look at the structure of water. It has H2O. Okay, so you have a draw the structure of water is, okay, HOH. Now H, okay, will go back to NH2 to form ammonia. So we are left with only OH. You do not have any Cl here. Therefore, okay, hydrolysis of amide will not go back to acyl chloride. You will get carboxylic acid instead. Therefore, okay, come look at the example of hydrolysis of amide. If I have this amide, okay, we use acid solution, you get carboxylic acid, okay. Here should be NH3, right? Don't forget NH3, ammonia is a base. It will react with the acid in the solution. So you get carboxylic acid and ammonium chloride. Again, just like hydrolysis of ester, amide can be hydrolyzed by using an alkali solution, sodium hydroxide solution. So if you use sodium hydroxide solution, remember you won't get carboxylic acid like in acid hydrolysis, because carboxylic acid is an acid. It will react with the sodium hydroxide in the solution. So you get a sodium carboxylate salt, okay, and ammonia. Now ammonia is a base. It won't react with another base, which is sodium hydroxide, so it will stay as ammonia. So remember, you choose, okay, you get to choose which hydrolysis you want, okay, which reagent you want to use for hydrolysis, acid hydrolysis or base hydrolysis. Your products must be consistent with, okay, the reagent that you choose. If you want to choose acid with water, okay, your products will be carboxylic acid and ammonium chloride. If you want to use sodium hydroxide, okay, after hydrolysis, amide will form sodium carboxylate and also ammonia. Now, both hydrolysis, you heat the mixture to 100 degrees Celsius. Basically, it's boiling the solution, right? Because hydrolysis means breaking of bonds, needs a lot of energy. That's why, okay, heating is required. Okay, right? Now, that's for hydrolysis of amides. We are going to look at the next reaction of amide, which is the reduction of amide. Now, we have seen this, okay, we have seen this for preparation of amines. Okay, if you go back to the first few slides on preparation of amine, okay, you will be able to see this one. Now, this is actually a reaction of amide. Amides can be reduced. So I have an example using general formula for an amide. Okay, if it is reduced by this reagent LiAlH4, you get an amine. Remove the O, okay, then add two hydrogen to the carbon. Now you see that, oh, it becomes R, N, and then another two R. So this is an amine. Now, depending on which amine you want to get, okay, you can just change the R to hydrogen, okay, or change the R to different R, then you get primary, secondary, or tertiary amine, depending on how many groups of alkyl groups, okay, uh, are bonded to the N. We have already seen this before, so remember reagent to be used to reduce amides, which is LiAlH4. Okay, and be able to write this equation. Okay, sorry, not this equation. I would say the product of the reduction of amide, which is an amine. Right. So that is all for the reactions of amides actually. Okay. Now we are coming to questions. Okay. Of course, I always included a few past year questions for you to practice from. This one is for a compound F. Now I chose this question because this compound F has two amide functional group. Okay, CONH, CONH. So hydrolysis of F will produce two compounds G and H. So why produces two? Okay, how to produce two? Since it has two amide functional group, then it should have four different compounds, right? But don't forget, you see, if you look at the structure, they are all connected. So by breaking the CN bond, okay, this part will form only one molecule, one compound, and this part another compound. So G, okay, they didn't say that you must G they didn't set, okay, say G must be the one on the left, H must be the one on the right. So that means G and H can be any of the products. So let's draw the left hand side one as G, the pentagon, CO, okay, and then I have the NH. Now remember, okay, I have to draw my products based on the reagents and conditions that I suggest, right? Let's say I want to use HCl, dilute HCl solution, and I want to heat it to 100 degrees Celsius. So if I use HCl, this CO part will become carboxylic acid, okay, but this NH here, okay, will become NH, 1, 2, NH2 positive. Okay, 1, 2, 3. Sorry, should be NH2 or NH3. Let me think. One nitrogen, NH2, NH3. Okay. Now let us look at the right hand side. Okay, just copy the other parts, they will not react. CO2H, then CH3. Now this part is NH. So you should get NH3. Okay, positive. Then this part will be C double bond O, OH. So this will be the two products of hydrolysis of compound F. Okay, so let's look at the answer from the mark scheme. So you see, you can choose whichever hydrolysis that you want to do. You can use acid, you can use base hydrolysis. So if you use acid, you can use HCl or H2SO4 sulfuric acid, but it must be dilute acid. Okay, that's why they put the N water. Must be dilute acid. So even if you want to use sodium hydroxide, it should be aqueous sodium hydroxide solution because you're talking about hydrolysis. Hydrolysis means you need a lot of water to be involved in the reaction. So it cannot be concentrated reagents, must be dilute, okay, or aqueous solution. And together with heat, now you see, they say if T is quoted, yeah, if you want to put a value for temperature, okay, please put 100 degrees Celsius. I choose the one in the middle so that it's always correct, not warm. Okay, warming is not enough to break covalent bond, so not just warm. Okay, and part two was the structures of G and H that I've already shown you how to draw. Okay, here they say allow protonated or deprotonated version, meaning if you are using hydrogen ion acid solutions, then you can protonate the NH2 to become NH3 positive. Sorry, this positive charge on the nitrogen. Okay, I want to make it clearer. Okay, so this is protonated version. The protonated version is for sodium hydroxide, meaning okay, COOH will become COO negative Na positive. This will also become COO negative Na positive. Here COO negative Na positive. I'm talking about if you use sodium hydroxide solution, right? This NH3 positive in sodium hydroxide solution is actually NH2. Okay, this is NH2. So that is what it meant by protonated or deprotonated versions are allowed, depending on the reagents that you chose. Okay, the next question, okay, I want you to pause the video to try to solve them. Okay, before I discuss, it is actually they give you the products and you're supposed to suggest a suitable acyl chlorides that is used to make the product together. Okay, you are given the other reactant, so you need to suggest the acyl chloride that is being used here. Okay, so pause your video, try to answer this question. All right, let's look at the first one. Look at this product E. It is an amide, okay, with two amide functional groups CONH, CONH. Then you are given NH2, NH2 is diamine here as one of the reactants. So some acyl chloride uh, was reacting with this diamine to form E, later become a cyclic compound, right? So can you see if I just have to number these two carbon as 1, 2, the carbon 1 and carbon 2, they are here. See, NH, NH was NH2, NH2. So that means the acyl chloride, okay, that reacts with this diamine has also two carbon because this carbon 3 and 4 must be from the other reactant. So just number 3 and 4 here. Okay, so they were acyl chloride, CO, CO, Cl, Cl. Okay, so that would be the structure of acyl chloride C. Now for the next one, it's harder because this is a polymer. It's actually from chapter 28, but I think that it's quite relevant to this chapter. That's why I included this question also. So you have a diphenol in this polymer. This was from this reactant. Like you see the benzene and the OH, OH, right? Became O and O. So H was removed to react. And then this part, this is from the acyl chloride. So the acyl chloride should look like this. Okay. The O in the middle is just a ketone, so you don't have to add Cl to anywhere. Okay, so this is Cl, this is Cl. So how do I know? Okay, this will react with the OH. So there's a byproduct here, HCl. The other side also reacts with another OH from another molecule. That's why at the end they all join together and form a polymer. Now we you when it comes to next chapter, okay, chapter 28 polymerization, you could have better idea about how this is formed. Okay. So for now, if you can understand the first one, okay, to me I think it's good enough. Okay. If you cannot understand the second one, right, I'll explain to you again in chapter 28. Right? So for now, okay, the most important one is the first reaction. You must be able to recognize the functional group in the product, okay, and know that, okay, they are actually formed from acyl chloride and amine. Okay, now it's about the same compound, still the same compound, the E. So it says that compound E dissolves in cold water, it does not react with cold water, it dissolves. By looking at this one, they want you to suggest the type of intermolecular interaction that occurs between E and water. Now imagine you have water, OH2, okay? H2O. This O has lone pair electrons. Hydrogen is bonded to very electronegative atom, which is oxygen here. So let's look at, is there any hydrogen that is bonded to electronegative atom in this compound E? Okay. Yes, the answer is yes. You have H bonded to very electronegative atom, nitrogen. So what is the interaction between this hydrogen and the O from water? Okay, hydrogen bonding. Then I realized that, whenever they ask for the type of intermolecular forces, most of the time, the answer is hydrogen bonding. So the first thing you check is whether hydrogen bonding can form between the molecule and also water molecules or not. Now, not just this hydrogen, okay, the oxygen here has lone pair also. So if you have hydrogen bonded, okay, the hydrogen in water molecule is bonded to O, so can also form hydrogen bond with the O from this amide molecule. That's why it's hydrogen bonding. Now, this part of the question is exactly the one that I've shown you just now. Why is amide neutral? They didn't tell you neutral, but they say, oh, pH 7. pH 7 means neutral, right? Why? It's because, okay, this is an amide, okay, and its lone pair electrons is delocalized. Please don't say that because amides are neutral. Okay, you cannot say amides are neutral, because if you say amides are neutral, you are just repeating the question. Question tells you that pH is 7. It's telling you that the solution is neutral. So you are supposed to explain why is it neutral and not to say that it is neutral again. So I put a bracket, okay, around the few words that I think you should put in the answer. Its lone pair is delocalized, okay, over the C double bond O. That is why, okay, it is neutral. It cannot be a lone pair electrons donor. Okay. Now there's another question on hydrolysis of a very interesting compound called carbaryl. Okay. Why is it interesting? Is because it will actually form, okay, three products when it is hydrolyzed. So first, okay, it is an amide because of the CO and H bond here. Can you see here? Okay, it is actually CO NH CH3. This part, okay, it is bonded to O, and of course the giant structure of these two benzene ring bonded together. So this CONH amide functional group. Then here C double bond OO. Can you recognize this C double bond OO? This is an ester. Amide and ester functional groups can be hydrolyzed. So when this is hydrolyzed, you are breaking two bonds, the ester link and also the amide one. So in the end, you get one product, two products, three products. That is why, okay, question tells you three products. So what are the three products? Let's start with the giant structure at the bottom there. Okay, this will be OH, alcohol, right? Phenol. Then left hand side, the CH3 and H, okay, will become NH2. Okay, hydrolysis of amide. Now, what happened to the middle one? Okay, middle one, the right hand side, okay, not the right hand side, the bottom, okay, is from the hydrolysis of esters, right? So you should add OH. Left hand side also add OH. So this one is actually H2CO3 carbonic acid that will easily decompose and give you H2O and CO2. So it's up to you. You want to write H2CO3 or you want to write H2O and CO2. Sorry, and CO2. Make it CO2. So three products, one, two, and three. Yeah, that is the reason why I want to show you this compound, because they combine amide and ester functional groups in the same molecule. Now you can try the other questions also. Okay, I didn't go through with you, and the answers for all the questions are on this page. So if you want to try the question, you go back and then you pause and look at the question and try to answer them. Then only you come and look at the solution to check against your answer. So that's all for amide in this recording. The next topic will be on amino acid. I think I'll do this amino acid in your next physical class. Okay, so today's recording will be three parts: preparation of amine, then you have reactions of amines, and also amides with their reactions.